Okay, now we're investing monthly, money monthly. It's compounding monthly, not continuously. So there is no E in this formula. So here's the formula. The account balance is equal to the principal times 1 plus the rate over the number, because we're doing it monthly, over M, raised to the time times M, or monthly, right? So we just need to identify each of the pieces. All right, so you invest 3,000, that's our principal. So we can go ahead and write 3,000, 1 plus, the rate is 7.5%. So if you move that 2 places, you have 0.075. If we're doing it monthly, there's 12 months in a year, and we're doing it 9 months. Well, 9 out of 12, 9 is the same thing as 3 times 3. 12 is the same thing as 3 times 4. Well, that's 3/4 of a year, or 0.75 times 12. Well, the 9 months. There we go. So now you're just going to, you could, if you had a teacher or professor that did not want you to use a calculator, at least initially, just simplify on the inside. Imagine there's an invisible 1. You're going to multiply top and bottom by 12, and then the denominator will be the same. The numerator, 12 plus 0.075, you get 12.075 raised to the 9th power. All right, and I'm going to plug that in. 3,000, left parentheses, 12.075 divided by 12, right parentheses, caret 9. And the amount in the account, when you're compounding monthly after 9 months, will be $3,173 and about 3 cents. So we could put an about right there. All right, that's pretty straightforward, not a lot to it. You're just going to have to be careful with converting that to a decimal amount. So if they would have said 4 months, how much of that of 1 year? Because remember, T is typically in years, so 9 months is 75% of a year. So that's where that comes from. All right. Now we have a bacterial growth or decay, and we're dealing with bacteria. The number of Streptococcus bacteria in a petri dish kept in a medical laboratory, and they give you this formula, which I've rewritten right here, where P is the initial number of bacteria and A is the final number. So initial, final, after a certain number of hours. And then they give you, if a culture containing 40,000 bacteria was brought in, how many bacteria will there be there after 10 hours and after a week? So let's do the 10 hours one first. So P is, we're going to use this formula, P is 40,000 times E to the 0.047 times 10. You can plug that into your calculator. 40,000, second ln, 0.047 times 10, close parentheses. And that is about 64,000 bacteria after 10 hours. Well, now we have to do it after a week. Well, a week is 7 days, and there are 24 hours each day. And remember, because the T is an hour, so we have to convert the week to hours. So 7 times 24 is 168. So now instead of 10, we're going to put 168. So 40,000, that was the initial, 0.047 times, Oh, I'm silly. I left off the E. Times e to the 0.047 times 168. All right, we're going to type that into the calculator. The number of bacteria will be, wow, so after 10 hours, it grows to 64,000. But after a week, or 168 hours, it grows to 107,460,589, almost 590. Yikes, that's a lot of bacterial growth in just 1 week. Scary. All right, now we have half-life problems. Radioactively decays according to the function. So here's the function. And the R sub O, I think, is going to be the initial or original. And then that's raised to e to the negative 0.004 times t. R sub 0 is the original amount. R of t is the amount remaining. So this is the remaining amount. That's the half-life. After t in years. So t is in years. So beginning with the 34-gram sample, so that's the R sub 0. So R sub t, we get 34 grams times e to the negative 0.004. How much remains after 15 years? So times 15. So R of t is equal, I'm going to plug that in, 34 second ln negative 0.004 times 15, close parentheses, about 32.02, but really it's probably, that's such a small amount, about 32. So beginning with the 34-gram sample, how much remains after 15 years? Wow, 32 remains after 15 years. That's pretty remarkable. Let's see if that, oh, and they actually left it to the 100th place. All right, that's interesting. Okay, temperature problems. The temperature of a 16-pound turkey, well, this is timely since Thanksgiving is just in a few weeks, in a 350-degree oven after T minutes. So T is in minutes by the function. Capital T of T in minutes is equal to 350, that's the degrees, minus 260 times e to the negative 0.001822 times t. Find the temperature of the turkey to the nearest degree after 2 hours. All right. And really, we could put T of 2. That would probably be a smart thing to do. And I'm just filling all this stuff in. And now we're going to put times 2. And you can type that into a calculator. So 350 subtract 260 times second ln negative 0.001822 times 2. And is this going to be in minutes? So 2 hours, we're going to have to type 120 minutes. Because that tells us 2 hours, but we want the t to be in minutes. So you're going to multiply that by 120 instead of by 2. So the temperature of a 16-pound turkey in a 350-degree oven after 2 hours, that will be about the temperature. All right. And we've already done some compounding continuously. So I think this is going to be it for this one.